Hi and welcome to the video. Today we take a look at how to calculate the Chodor form of a matrix and how to calculate the matrix exponential function from that. Here's why we're doing that. The Chodor form is the closest we can get to have a diagonal matrix for a matrix that is not completely diagonizable. As example, when its calculation is required is, if you try to calculate a discrete system matrix representation, like we did in last month's video by hand. For the video here, I chose a particularly nasty matrix where we have to take an extra condition into account when it comes to calculating the generalized eigenvectors. The video is split into the following parts. We begin by looking at the step-by-step overview how to calculate the Chodor form, and afterwards we cover the individual steps. First, how to calculate the regular and, more important, the required generalized eigenvectors. Then how to assemble the transformation matrix T and the Chodor form J. Towards the end of the calculation example, we consider the calculation of the matrix exponential function of the Chodor form. After the calculation example, I will address details regarding the calculation of larger matrices. We close the video with a brief summary and outlook as always. Here a short recipe how to calculate the Chodor form of a matrix. First you calculate the eigenvalues. Then for all the eigenvalues the eigenvectors. If an eigenvalue appears 2 times, you also get 2 eigenvectors and you are done. If that is not the case, you have to start calculating the generalized eigenvectors. It is required if the geometric multiplicity of an eigenvalue, so the number of eigenvectors, is smaller than the algebraic multiplicity of the eigenvalue, so how often the same eigenvalue appears. For example, if eigenvalue lambda 1 appears 3 times, we have algebraic multiplicity of 3. If there are only 2 eigenvectors for lambda 1, we have geometric multiplicity of 2. Since the eigenvalue appears 3 times and we only have 2 eigenvectors, we have to calculate one additional generalized eigenvector. After calculating all the eigenvectors and generalized eigenvectors, we can assemble the transformation matrix T from them. Finally, the Chodor form can be assembled either directly using the rules based on the number of eigenvalues, eigenvectors and generalized eigenvectors, or simpler just by calculating it with the equation inverse of T multiplied by the original matrix multiplied by T. Both give the same result in the end. In the very last step, the transformation matrix is used again to calculate the matrix exponential function of our original matrix A using the matrix exponential of the Chodor form. Please note that for most of the calculations, I will just show you the start and end matrices, but we will not go through how to calculate everything step by step for time reasons. You can always pause the video to calculate along either by hand or with MATLAB. Let's start with the calculation of the eigenvalues. As mentioned before, this is the matrix we use for the calculation example in this video. The eigenvalues are the solution of the characteristical polynomial, or in other words, the solution of this equation here, where we solve for lambda. For this matrix we have 2 different eigenvalues. The eigenvalue of 3 appears 3 times, so the algebraic multiplicity of the eigenvalue is 3. The eigenvalue of 5 appears 1 time. If all eigenvalues would be different, we would already know that the matrix is diagonizable. Since they are not, we do not know if the matrix is fully diagonizable or not. It could be, just because we have algebraic multiplicity greater than 1 does not necessarily mean that we need the Chodor form. For a counterexample, this matrix over here has the exact same eigenvalues, but it is fully diagonizable and you would not need the Chodor form. But since we do not have that matrix, but this one over here on the left, it is a bit more complicated. To figure out if we need the Chodor form, we start by calculating the eigenvectors and, if required, the generalized eigenvectors. To calculate the eigenvectors, we solve the equation lambda times the identity matrix minus our original matrix A in brackets times the eigenvector xi is equal to 0. We solve for xi for both of our eigenvalues. Running through the Gauss elimination for the eigenvalue lambda equal to 3 leads to the matrix multiplication shown here and the eigenvectors here. Since we only have geometric multiplicity of 2, we have to calculate a generalized eigenvector. Without it, we would not have enough vectors to assemble our transformation matrix T. For this specific example, we could at this point already say that our Jordaan form looks like this here. For our eigenvalue of lambda equal to 3, we have two eigenvectors, so we know that there are two Jordaan blocks, and the only possibility how this can look like is if we use a 2 by 2 and a 1 by 1 block. The last eigenvalue of lambda equal to 5 has algebraic multiplicity of 1, so it is also a 1 by 1 block. Since we need the transformation matrix T to calculate the matrix exponential function of the original matrix, we will proceed with the calculations and calculate our generalized eigenvector. The equation to calculate the generalized eigenvector looks like this here. Eigenvalue lambda times identity matrix minus A multiplied by the generalized eigenvector is equal to another vector xj. And here you have to be extremely careful. In a lot of cases you are able to just use one of the eigenvectors on the right hand side of this equation. But in general, and also in this example, you cannot do this directly. Let's first check out why by running through the Gauss elimination using both of the eigenvectors calculated before. For the first eigenvector, the resulting system is shown on the left-hand side, and for the second on the right-hand side. You can see that you can't solve the resulting system of equations for xij just by looking at this row here. So with this choice of vector on the right-hand side of the equation, it is impossible to calculate the generalized eigenvector. For the choice of xj, we need another vector so that the resulting equation can be solved. Since a linear combination of eigenvectors belonging to the same eigenvalue is also an eigenvector, we can try to find a suitable linear combination. So we have to find xj that leads to a system of equations that can be solved. The requirement for this is that the rank of two matrices is equal. The first one is just the matrix resulting from eigenvalue lambda times identity matrix minus A, and the second one is the matrix resulting from lambda times identity matrix minus A with our candidate vector xj appended on the side. Without going into mathematical details, it is easier to simply show what this means in practice. The calculation of the rank is just running through a Gauss elimination and counting the number of rows that are not completely filled with zeros. So let's do that for the two eigenvectors where no solution exists and write the matrices down and mark the individual parts. In red, the matrix of lambda times identity matrix minus A with rank 2, and then in the second color, the full matrix where we see that the rank increases since we have an additional row that is not completely filled with zeros. If we bring the equations from the previous side back, we can see that the increase in rank tells us that we now have a system of equations that cannot be solved. Since we would have to have a solution for this row, if the rank stays constant, however, we still have a 0 over here at this location, and thus a system of equations that can be solved. That is why the rank has to stay constant. In order to solve the equation and calculate the generalized eigenvector, we can try a different candidate for xj, that is a linear combination of our two eigenvectors, and run through the same calculation. Let's first check the rank and look at the Gauss eliminated result of our matrix. We see that the ranks of those two matrices are equal, and this results in a system that we can actually solve. So let's do that. And we get the vector here as generalized eigenvector. Now for the last two steps. First calculate the eigenvector for a second eigenvalue of lambda is equal to 5. First the Gauss elimination, and afterwards solving leads to this eigenvector here. At last, we can assemble the transformation matrix T and calculate the Jordaan form J of the matrix. I will just put the finished Jordaan matrix up here for reference while talking about the assembly order so that I can point to the resulting blocks. We first use the candidate xj that we use to calculate our generalized eigenvector. Afterwards, we put our generalized eigenvector. Those two lead to our 2 by 2 Jordaan block, the one from up here. then the last eigenvector for lambda 3. We can use any combination of the original eigenvectors calculated for lambda equal to 3, with the only exception being it has to be different to xj that we used for the first one. It can also not be xj scaled linearly. I just used the first eigenvector v1. For the last entry, we use the eigenvector for lambda equal to 5. Those last two lead to the Jordan blocks with size 1, so the blocks where we just write down the eigenvalues directly. For the Jordan blocks of size larger than 2, you just start by putting more 1s on the second diagonal. So if we only had one actual eigenvector and two generalized eigenvectors for lambda equal to 3, we would have another 1 here. I have another example later on showing larger Jordan blocks. However, the nice thing here is that you would not even need to remember how to assemble the Jordan form like that, and where to put the additional ones, because after assembling the transformation matrix T, you can calculate the Jordan form directly using inverse of T multiplied by original matrix A multiplied by T. The order of vectors has to be correct, so the blocks are created correctly. I hope that is obvious. Feel free to use different linear combinations of vectors. For example, the last eigenvector can be scaled arbitrarily with the parameter t, and the Jordan form doesn't change. Try it. The matrix T can have many different forms, but together with its inverse, it will always lead to the same Jordan form. If you want to calculate the Jordan form in MATLAB directly with numerical means, you can use the function shown on screen right now. To calculate the matrix exponential for our original matrix A, we compute this equation here, where we use the transformation matrix and its inverse together with the matrix exponential of the Jordan form. The matrix exponential of the Jordan form is calculated blockwise. In general, for each Jordan block, we insert a matrix that looks like this here. It is assembled with the following structure, starting from the left to the right in the first row. Each entry is calculated with tau to the power of k divided by k factorial and then multiplied with the exponential function to the power of the eigenvalue times tau. As we go from left to right, we just increase k by 1 each time. For the first entry, tau to the power of 0 is 1, which is divided by 0 factorial, which is also 1. This leads to the regular exponential function to the power of lambda times tau. And afterwards, we just increase k by 1 each time as we go from left to right. Then we copy this entire row down, shift it to the right by 1, drop the rightmost entry, and fill the rest with zeros. This is repeated for the entire matrix until it is square. If you now need a 2x2 block, you take the upper left 2x2 block of this. If you need a 3x3 block, you take the next bigger one, and so on. For our single values, so the 1x1 blocks, we insert just this first part here. If we have a fully diagonalizable system with only 1x1 blocks, we end up simply inserting the exponential functions of the eigenvalues on the diagonal. Let's apply this to calculate the matrix exponential function of our original matrix A. We start with the Jordan form and its matrix exponential function. This here in red is the first 2x2 block for the eigenvalue lambda equal to 3. This in blue, the next 1x1 block for lambda equal to 3. And finally in yellow, the last 1x1 block for the eigenvalue lambda equal to 5. As you can see, all the remaining entries of the matrix exponential function of the Jordan form outside of our Jordan blocks are simply filled with zeros. The matrix exponential function of the original matrix A can now be calculated by multiplying with the transformation matrix and its inverse, written down as matrix multiplication down here. There is something I have not covered in this video, and it is the following. Say we have a 7x7 matrix with eigenvalues all equal to 2. The first calculation gives us only 3 different eigenvectors, so we have geometric multiplicity of 3. I have put a few possible Jordan forms for a matrix on screen that could be the result in such a case. For a scenario like this, we have to figure out our size of the Jordan blocks, since there can be multiple solutions. we could have a 5x5 and two 1x1 blocks, or a 4x4, a 2x2 and a 1x1 block, or two 3x3 blocks, and so on. And in addition, we have to calculate all the required generalized eigenvectors afterwards. If you would be interested in this, please tell me in the comments or upvote comments that ask for it, so I know that there is actual interest in a video for it. For a quick last thing, showing the matrix exponential for a larger Jondor form, where we need multiple blocks. Here we have 3 blocks. I will mark the blocks and the corresponding entries in the matrix exponential function for the matrix. We have the first 4x4 block for the eigenvalue of 2, here marked in red. Then a 1x1 block for the eigenvalue of 3, marked in light blue. And finally, the 2x2 block for the eigenvalue of 5, marked in yellow. Okay, thanks for watching until the end. Quick summary to close the video. We covered how you can calculate the Jondor form of a matrix, required if you want to calculate the matrix exponential of a matrix that is not fully diagonizable by hand. We took a look at a particularly nasty matrix that requires an extra step when calculating the generalized eigenvectors. I still want to do some more research on the calculation of Jondor forms myself, especially when it comes to bigger matrices. And if there is enough interest, so show it in the comments and likes, I will make a follow-up video. Currently, I do not know what the first video of 2026 and the upload schedule will be. There will most likely be some changes to the upload schedule. I would like to do something with actual hardware and go more into the direction of practical control engineering. If you found this video helpful, interesting or entertaining, let me know in the comments and by hitting that like button and share the video. Thank you very much for watching, have a nice Christmas, bye for now.